Today's speaker is Anastasia Kadadi. She's a PhD student of our department. As you can see, the title of her talk is RGB-Depth Image Segmentation using Interproximation with Cubic B-Spline Curves. The work that will be presented here is a modular algorithm for edge detection and image segmentation by integrating local and global techniques for processing RGB depth data. This is the first part of our thesis here. The algorithm that she will be presenting here strategically employs a hybrid approach using interpolation and approximation techniques to address the data uncertainty problem and to construct an optimal curve that accurately represents the object's boundary while ensuring the smooth shape by minimizing its global image. So let's welcome our speaker for today, Anastasia.
Well, thank you so much. Thank you, Dr. Chiang, and thank you for inviting me here, Dr. Chiang. And I'm glad to see old faces, new faces. I think my face is getting old as well. Shortly about myself, I got my bachelor's degree here at University of Kentucky. I was in a scholars program, transferred to master's program, transferred to PhD program, and I'm at the end of my education here. So hopefully this is the last semester for me, and I will defend my thesis at the end of April. I currently work at Eastern Kentucky University as assistant professor, and I teach 3D modeling and game design. And I also oversee game development club and virtual reality club and multimedia concentration at EKU. So this paper is RGB depth image segmentation using interpolation technique with Cubic B-Spline Curves. So what I'm going to talk about is a two-dimensional case, which is essentially can be extended to a three-dimensional case. So advance in development of high-grade commodity RGBD sensors. RGB stands for red, green, blue channels, and D stands for depth. It has shaped a landscape of computer vision in the past years, and related goals that we have in computer vision and tasks, they have been changed, and they're constantly evolving. Integration of this kind of data for image segmentation plays pivotal role in advancing computer vision application by providing more accurate representation and semantic interpretation of visual scenes. So here on the right-hand side, I have various depth sensors. But this application is not only restricted to depth sensors, also to different camera setups, including towed-in cameras or stereo cameras and other custom setups that could be used to infer depth data. Importance of newly developed methods lies in combination of RGB information from color images or from RGB images with the depth information that we can get or infer somehow from those images. And this paper that I'm presenting, it focuses on using depth data to solve edge detection and segmentation problems. So This algorithm is modular algorithm that solves both problems of segmentation and edge detection by employing local information, pixel-based data processing, along with global methods of interproximation for boundary smoothing. And we simplify the task of segmentation to task of edge actually detection of outlining boundary of entire object. So here I have a few of the stereo cameras examples. So the contribution of this paper is in employing local approach for semantic pixel classification before and after edge detection, and global approach to estimating edges by minimizing energy of a curve representing boundary of an object. So I will look at this algorithm step by step as it would process the data. And the first step is the initial guess of boundary of an object. So I am we are using here pixel-based classification of depth, and this is the foundational step, and this would be our initial guess where the object boundaries would lie in the scene. So each pixel in a depth, either in disparity map or in a depth map, corresponds specific or represents a specific distance from camera to the objects in the scene. And user will select a point. Well, you can do it several ways. You can do it automatically without user input. Here, at this point, I have my algorithm starts with user input by selecting a point on the image. So we start with the point on the image and expand the search for boundaries in all 4 directions. So, for example, this is a subset of depth values from my image, and I would search for the boundary of an object in all 4 directions. And here, I would say this is the boundary representing all sort of uncertain pixels between an object that I'm interested in and the rest of the scene. So I will search in all 4 directions. All 4 directions for the boundary. And the boundary identified simply by the difference between depths in object versus pixels from other objects. And a lot of times you will have difference and you can set up threshold value for this difference and identify objects in that way. So during this expansion, pixels are classified according to a predefined scheme, and I will show you what that scheme is. It's pretty simple. And we assign some labels to each pixels to identify that pixel belonging to some class, classification class. Output of this step would be a comprehensive classification matrix, and that would contain the labels for all the pixels along with the boundary of that object. So I will cut out that object from depth image so that I can focus on that area. So the bounding box is also will be recorded for that object. So here, all of my semantic labels, I would say I will assign -1 as a label when there are depth values that are undetermined. And depth values that are undetermined come from failed signals or from occlusions by other objects, or you would get also jagged edges of objects. This is where the uncertainty would come from. 0, I would identify objects, other objects, by assigning 0 label to those objects and just saying, letting know my algorithm that that does not belong to the object. 1, I will identify this as an object itself, and 3 would be my initial guess for the boundary, and 5, I would surround holes or sort of where my depth is undetermined. I would surround that also by specific labels such that I can fill in those holes later on. So now that I told you that I'm expanding or I'm looking in the image in all 4 directions, then you would say, oh, this is pretty simple, right? So look everywhere and just say, okay, this pixel belongs, this pixel does not belong. However, you have 4 directions, and if you want to write logic for that, it is redundant, right? Because you will treat all the directions sort of the same, but if you make logic mistake someplace, it's really hard to follow, really hard to keep it uniform. So what our algorithm does, it actually avoids unnecessary redundancy here and complexity by rotating image, right? So I will treat all the directions as one. In this case, you can choose any of the directions. We chose right direction, and I will, the image will be rotated to line up with that direction, and classification will proceed. So here I have the original orientation, and I would rotate my image either by 90 degrees, by 180 degrees, or by 270 degrees, so that I treat classification as a single direction. So before attempting classification, we would rotate the image. After classification is done, rotate the image back to original orientation. So here's the guesses, samples of guesses of objects done with this algorithm. Then we go to the next step. In this step, we want to construct a list of points and regions. At this point, I have an area that has no order, right? So I will just have a bulk of data that will tell me that some pixels belong to objects, some don't, right? So, but for the next step, we have to organize data in a way that it's an ordered list, right? So one point comes after another. And in this step, this is what the algorithm does. It goes through this classification matrix, and it would construct an ordered list in this way, right? So we have a sliding window. We slide the window through that classification matrix, and we find the first edge pixel, which is identified by label 3. So then we follow those pixels along the edge by sliding that window along the edge and record all the pixels in that way. So this what this part does. And again, we search for the next boundary pixel within this sliding window. And as we find next pixels, we will mark it visited. So we do not repeat that process for pixels that already have been visited. Classification matrix will be traversed until no more boundary pixels are detected. Output of this step is a large list of all the points and all of the uncertain regions within this classification matrix. So after this, so this classification matrix, I put this image serves also sort of as a mask for an image where the object, where our initial guess for the boundary would be. So this classification matrix also serves as a mask. However, we need, in the next step, we have to downsize the data because we do not need all of the boundary pixels, because a lot of times you will get hundreds and thousands of points if the object is large. the algorithm actually that detects the boundary or approximates the boundary don't need this many pixels. So in the next step, we want to downsize the data. And this process is guided by curvature of the curve that this data represents. And how is it done? If the curvature is pronounced, then we get more points, right? So if there is a sharp turn in the edge, you want to get all the points such that you approximate that edge more carefully or more precise. And then we will we would select less points if the curvature is not large. So once all the necessary points and regions are selected in this manner, we will store this as a text file to be the input to the next step of the algorithm. And the next step is interproximation algorithm. So to assist, to actually to give us a good approximation and a smooth boundary of a curve, we'll employ this method. And in this method, we use Cubic B-Spline, and we want to approximate given data with this method that combines interpolation and approximation techniques together. So let's talk about this really briefly. With interpolation, if you have data points and you want to fill in all the points in between, how you do that? You can employ any of interpolation techniques. Here we will use B-splines, and your curve in this case have to pass through all the given points. So here would be an example. You have 5 points, and you want to compute points in between those points. Those are the separate dots on the curve. You would use interpolation technique to do that. However, interpolation on its own is not suitable for the data that we deal with when we work with depth data. Therefore, we will use also approximation technique. And approximation is a data fitting method that perform data fitting by backwards error analysis, and does not guarantee that resulting curve will necessarily pass through the points. But we can, I will explain later how we will guide this algorithm to actually perform in the way that we want it to perform. So here's an example. Here I would have some data points and some regions. So the curve itself don't have to pass through the points. It just has to pass through those regions to approximate that curve. So here I still have the curve that passes through the points, sort of, but if you specify a different point that is not on the curve, right, so it can approximate it without passing through. So this is an approximation technique. So again, utilizing a single method is not suitable, so we will combine these two into a hybrid method. Interproximation and would contain interpolation and approximation techniques. So the resulting curves will interpolate the exact data. Yep. Well, if you constrain your algorithm to pass through a certain region, it may pass through the data point that could represent a center of that region, or it can pass anywhere in that region.
So just like brushing against the corner is enough?
Yeah, okay. It will be good enough.
Okay.
Yeah. But there is a condition for that as well. And I will, if you're patient enough, I will talk about the condition. All right, so interproximation will ensure that it will pass through exact points, and it will pass through the uncertain regions where we do not know where the depth value should be or what object it belongs to, whether or not it belongs to object in the front or in the back, or it's the object that we are looking at. So it will pass through those regions in a way that it will minimize the energy of the curve for each of its piecewise curves. So here I have the red dot would represent my exact points, and the green boxes would represent my uncertain regions, and that curve will actually pass through those exact points and through the regions in a way that the energy of this curve is minimal. So the algorithm itself is as follows. So given a data set of points, I will denote them as depth I, and those will contain all of the exact points and all of the uncertain regions. So exact points, I will call them depth ij and also pj. And for each of the point, I will have x and y value, and all of those will be in a set of from 1 to n, and this set will represent exact points. And uncertain regions will be represented by the centers of those regions and offsets where it starts, so left-hand side and top left corner and bottom right corner. And those regions will be denoted by a box where you have two x values, where the region starts, where the region ends, and two y values where region starts and where region ends. So for some of the uncertain points, that would contain just single point, or some arbitrary shaped rectangle. So here's an example. If I have a cluster of unknown depths, I will include them or box them in a single region and represent that region by 4 values, 2 x values and 2 y values. And this set will go from 1 to m. So if I have 10 exact points, I will have exact points go from 1 to 10. N would equals to 10. If I have 15 uncertain region, my points would go, or regions would be counted from 1 to 15. So for conventional or a traditional interpolation method, we will need n plus m points, right? So this is our case, n plus m points, where n represent number of exact points, m represent number of uncertain regions. For an open curve, we will need n plus m minus 1 line segments. And for closed curve, we will need n plus m curve segments to represent the entire data or interpolate the entire data. Also, we will need m plus 2 contributing basis functions because we're using B-splines. And those basis functions will be of degree 3. And before we perform interpolation, we will parameterize the space, and we will represent that space by n plus m plus 6 parametric knots. 3 extra knots will be included because of the contribution from basic B-splines that starts before our first knot and after our last knot. And we will represent parametric knots by a set of T And our t will start from -2, so extra 3 knots at the beginning and extra 3 knots at the end. So B-spline in itself has a recursive formula, and it has a base case, which is will be hit by reducing the recursive case by reducing the degrees of the contributing basic splines. And when I equals to 0, it will have value 0 at that point. So you can think about this as a step function, and it would have a value of 1 at the knot where it starts. Everywhere else, it's going to be 0. So all the other curves, by the way, here, it's a curve of second. So this is 0 degree, first degree, second degree, and third degree. Now let's go to recursive formula. And the recursive case is computed by splines, by 2 contributing splines of lower degree. So for this system of equations, and we would like to solve the system of equations such that we find our control points. So for this system of equation, we will have n plus m plus 2 B-spline curves that will contribute to the interproximating curve. But we only have n plus m fitting condition because that is how many points we have. Like in the traditional interpolation, we will introduce 2 additional conditions by saying that second derivative of this function at first and the last knot has to be 0. And we will incorporate that into the formula for our B-spline. So the final formula, and we will call our function f of u, where u will represent a parametric knot. We will define it as follows. We have 2 parts, and the first part will correspond to interpolation, where we compute a curve that passes through all the points. And I will explain all the components. And the second part on the next slide, and the second part is the part where we're going to approximate all the regions. So alpha I and beta j are the 2-dimensional control points for the curve. And if you've studied interpolation, you know that if you change the value of those knots, you can actually modify the shape of the curve. So, but this is actually what we are wanted to solve for our system of equations. And gi and hj are the basis functions of degree 3 contributing to the curve. And our parameter range, we will do parameterization from t1 to tn plus m. So we have for our condition or for our interproximation technique, we have 2 conditions. First condition is our curve f of tij. So at the knots where our points are located, we have to, our function has to pass through a point. So for that knot value, you should, as input, you should get, as output, you should get the data point that was the input to this function. And then for approximation, we do not need to pass exactly through the point, so we just need to belong, right? So we should pass through that object or through that rectangle, and rectangle we will define it by xk by yk. So it has to, it has to belong to this region. So these two conditions have to be satisfied, but as you have noted, right? You ask the question, how does it, in what way will it pass, right? So brushing off would be good enough. Yes and no, because it actually, if we allow it to interproximate in all kinds of ways, or we don't restrict the function, it can give us different approximations for those regions, and the number of those approximations is infinite, right? So just like there is infinite number between 0 and 1, we would get an infinite number of possible curves that we can produce here. So we will restrict it by optimizing this problem by finding minimum energy of that curve at each of the line segments. So there will be just one curve that will have minimal energy. So, and this is the curve that we are seeking. But that curve also have to satisfy both of our conditions, interpolate all exact points and approximate all the uncertain regions. So, and the energy of the curve is defined by integral of the function of the second derivative squared, and this is the function that we want to minimize. So the next step, this is where we come into the next step. Once we have constructed the function that will interproximate our boundary, we want to minimize that function. And for this step, we will use nonlinear programming, and we will constrict or restrict the function by bounding regions. We will say, okay, find me a minimal curve that passes through all of those specified regions. Here's the result. You can interproximate any kinds of data, any kinds of curves. Again, for these kind of regions here, or in antlers here for the deer, you will have to provide more points for the curve to approximate, more accurately pass through those points, and less points when you have almost like a straight line. So in the last step, so far what we have done, we have guessed the initial boundary, then we estimated the minimal curve for that boundary. Now we actually need to fix what we have in the actual depth map, right? So how we do that? We will perform a depth adjustment, and depth adjustment will target 3 different types of values. Those are false negatives, false positives, and uncertain depth. Well, false negatives, what are those? Those are depth values that were initially identified as not being on an object, but after interproximation, they should be included within the object. False positives, those are the depth values that initially been identified as being outside of an object. Being initially identified as being or belong to an object, but they're actually outside of that boundary of that interproximated curve. So here, with the false negative, we have to add them to the object. With the false positive, we have to remove them from the object. And the last type of data we will target is the failed signals data or occlusion data, and we will also replace that data as well. So the depth adjustment is performed by weighted differences mean algorithm, and here's how you would compute it. And each of the weighing coefficients here, Wi, is computed by inverse mean between current depths and the depth chosen from the neighboring, from closest neighborhood, basically. So here's how you would compute all the weights. You would compute a sum of differences of those weights, and then you would use those weights within this formula. So why is it good to use this method? Is because this method is less sensitive for outliers. And since we have sensors that will assign depth values according to the readings that they get. Sometimes these readings are faulty. Even though it's within the boundary, it could still be faulty. So this method is less sensitive to this kind of data. So here's the result. Here's the image depth data from inferred from that image. Smoothed image and image overlaid with RGB. So I wish I should have probably made it a little bigger. So here, for example, we had uncertain depths represented by values of 0 in depth, and then some jagged edges. And after smoothing, we actually restored all the missing depth and smoothed all the edges. Same, I just showed you different regions. All right, so completed remarks. For the future, yeah.
So, if you don't mind going back, I noticed, I'm confused about how two things are interacting here, because I noticed it was interesting that your ability to detect the edge was going behind the occlusion here, right? Capturing the back of the bus. But
So here's the occlusion, right?
right.
Yeah.
And so you found that your desired shape is behind that occlusion, but then you're talking about finding things that you read the wrong depth of or need to include within this region. So how do you know not to include this occlusion?
Because it has different depth. Right? Because this object over here is in front of the object that I'm interested in.
Yeah, like I guess my confusion is since you're saying some of the readings are going to be wrong, right? Is it just, well, so many of these readings are that this is in front, that not all of these are going to be wrong. It's only going to be wrong in small amounts, and so you smooth up the small amounts, but not the large difference. Does this make sense?
Not like I'm not sure if I'm understanding the questions. You're saying how do I know to how do I handle this? Well, I would consider depth. Well, in this algorithm, I'm interested in outline, right, of an object. How I know it is an arrow, because the arrow values actually will be either 0, 1, or 2 or 3 really low values. Well, that will differ for different sensors, but they usually are really low values that they drastically differ from the depth values for other objects. All right, so future works here would include extending this to a 3D case where you actually smooth the actual surface of an object to represent that object, and actually use some of the RGB data or lighting to superimpose details on the object. So what you can think about is that depth values are quantized values between, well, for different devices, they will be different, right? So, for example, for depth, for Kinect, is between 0 and, for different versions of Kinect, it's different. But your values are going to be within 0 and 1,000, for example. For other depth sensors, they will treat that as something else. But again, you can think about that when you reconstruct, right? When you reconstruct and represent that surface with digital model, then your model doesn't need to be quantized, right? So it doesn't have to have specific values where if I have 0.5 depth, right, it falls between, or if I have a depth of, for example, let's say, okay, 0.5, right? So whether do I assign that depth to a 0? Do I assign that depth to 1? So there will be a scheme how your sensor will treat that data, but it will assign only integers to the depth data, right? So however, in the model that we restore, or we will model to represent the object, we can have all kinds of resolutions for that object, right? So we can have original resolution, or we can increase the resolution. So in the next step, or an additional research, would be increasing the resolution of this object. So, and all the, you know, speed is an issue here, so I would consider either using GPU or using parallel computing, and some other options. So they have some references, questions, comments.
Okay, so I've got a couple of questions basically relating to resolution. No. If you go back to your picture where you had the example there. Yeah. So, well, there are two kinds of resolution issues that I'm wondering about here. So one of them is that if you take a look at your depth data, I'm seeing something that looks like a sculpture there. It's got three-dimensional details for the ear, et cetera, and all those are gone. So
it's not gone. You just don't perceive that, right?
Well, that's the question.
With the way I
are those surfaces actually being taken as surfaces, or are you basically just taking flat planes? Basically, I guess what I'm saying is it's 2.5D as opposed to a 3D
This is
level.
a point cloud at this point. You can think about it as a point cloud.
Yes, but what you're getting as your edges,
yeah,
you're grouping those things together in some depth ranges, right?
Well, I can compute any depth range for, I can compute any number of points in between the points that I have.
So what I'm getting at is, so why don't I see an outline for the ear, for example? And actually, before you answer that, let me give you the other part.
Okay.
The other part is that there's the spatial resolution issue in the two-dimensional plane, in that your color image is often higher resolution than your image of the depth. So you can get some detail about where the edges actually are that's coming from the color image that you can reflect back into the depth image.
That's correct.
So I was wondering how you're dealing with that.
That's correct, and that would play a role for 3D reconstruction. In this particular case, the purpose of this is to compute the segments of the image, which will represent the entire object. So this is why there is no outline for an ear, because that was not the purpose. The purpose of this algorithm is to get an outline of an object. For example, if you're flying, you avoid the object. So whether or not there is an ear, it's not really important. So a different usage of the data or the results in this particular case. And yes, RGB data has more data than the depth. Again, at this point, it is not a purpose of the algorithm. Yeah. Yeah.
Oh, I was going to ask, how does this perform on transparent objects? I mean,
Transparent object?
yeah, like if you have a glass sphere, because things are deflecting through or diffracting through. So does it really take edges from there?
Actually, I have not tested it. That's a really good point. I have not tested the algorithm for this. However, again, I'm starting this from data that is available, right? So if the depth data is presented to me in a certain format, it is like I will not change the depth data.
Yeah, because then for like transparent objects, the radiance come into play. So then because the whole your whole algorithm is very dependent on how you capture the data.
Yes.
So for example, suppose there is a line and that is supposed to be the edge, and it misses due to some like overexposure or something, the line breaks in between. But if that break, like start of the line and the end of the previous line, if the distance is too high, can the B-spline approximation connect it?
Okay, so you are talking about RGB images. So depth data is different from RGB. The exposure is not going to play a role in depth data.
They are okay. Even if exposure is
In some of
overexposed.
cases, yeah. But also, I did not tell you this, but this algorithm aims at capturing faces. So there are certain assumptions that are made as well.
Oh, okay.
Any other questions?
I can probably do it without the. I have this. I just wanted to ask about the. You mentioned wanting to improve the speed, but I wanted to ask, like, for that image that you were showing earlier, like, how long did the whole process take on that?
Well, I do use some of the parallel processing, but it's limited. I think MATLAB can only allocate a limited number of workers. So I do have some parallel processing in interproximation part of the algorithm. Depending on the number of points, it can run between few seconds to few minutes.
Mm-hmm.
So if you have a large object, that's why it's important to get the curvature values and get more points when the curvature is high and drop the points that you don't need.
Right.
You have to see a few things about the pure processing here, that if you have GPUs that you can use, you have two approaches. You can use, you can write compute shader program, so that you can use all the force provided by GPU. The GPU sometimes can provide as many as 4,000 cores. And if you have 1,000 GPUs, your computing power is huge. But you have to know how to use compute shader programs with that. Or, use CUDA. CUDA is not cross-platform. GRSL allows you to cross-platform. So I would say computing is a better approach. We still have to.
Again, this is a prototype. It's not the, it doesn't reflect the final product.
Hey, I have a question about the first step, the initial guess. And could you turn the slides where you have that matrix with all the labels, like the zero? Yeah, this one. So here, this matrix, it shows like every pixels here. I mean, each number here, X, I, G, is for every individual pixels.
Yes.
Okay, so your initial algorithm, you are like trying to traverse each of the pixels, right? So
Not each pixels. I will start within the object that I'm interested in, and I will
then you
expand
have
them
these
with.
4 directions.
Yeah.
But still, in the end, you have this map.
Oh,
like
how do I end? I do not expand in a certain direction if there is no more pixels to explore for that particular object. So if all of those, if all of those are -1s, well, if all of those are negative values, this is where I stopped. If some of them, they're still labels that identified belonging to an object or might belong to an object, then I will still continue expanding in that direction.
Oh, okay, I see. So, yeah, okay. I was wondering, like, here in the matrix, for example, there you have, I mean, in the lower part, all of them, they are labeled by 1. So perhaps, instead of going through every pixels, you can have some sort of like sampling in order to speed up the process.
Of course,
Of-
you can follow age as well. When you do this, you can start with an age and
Yeah.
follow the age because you know the age should be continuous, right?
Yeah.
Like you will make an assumption that object has a continuous age. So you can follow the age instead. I chose this method.
Okay, I see. And how did you choose the initial point? Like you have to.
It can be chosen arbitrarily, like random choice. You can go through image. You can iterate through image through all the objects in the image, but you have to start someplace, right? So you can randomly choose an object and go from there.
Okay.
Yeah,
And also,
in this particular prototype is user chosen point.
okay. And also for the labels, like here you assign 0, 5, -2. These ones is according to some schema.
Yeah.
This schema is manually defined or?
Yes.
It's manually
It's just
defined.
assumptions. It's like, okay, if not assumptions, but I will say, okay, if there's a hole,
Yeah.
I will say all the labels around that hole will be 5. If
It-
there is an object between, let's say, if this is my pixel that I'm looking at, and well, this is the pixel that belongs to the boundary, and next pixel doesn't, I will label it as 3.
Oh.
So like you can label them anything you want, characters, letters, anything. It's
Yeah,
just
yeah,
internal identification.
Yeah, I'm just wondering about the schema you define here. So it's not based on the RGB value. It's based on how the relative distance from what you are looking for.
Right. So this is all based on depth values. Yeah.
Okay. Thank you.
You're welcome.
Okay. Maybe this is beyond the scope of your research, but how well would this work if it's like, let's say, 2 sheets of fabric that are both really wrinkled on top of each other? So then the depth would be kind of very similar, and the edge will be, I would imagine, quite difficult to detect. Have you tried anything like that?
Well, I am not trying to cover all possible cases in the world, right? I'm trying to detect or reconstruct human faces. So again, this is a really narrow purpose algorithm. And of course, in a human face, you're not going to have that kind of texture differences. Yes, great question.
So many years ago, this would be back in like the late 70s and early 80s, basically this was referred to as the edge linking problem in image processing. So I'm wondering, how different is what you're doing from what was used way back then?
Well, back then, we didn't have depth sensors or didn't use depth sensors in computer vision. It's probably last 10 to 15 years that that trend emerged within computer
But you
vision.
still had edges.
Yeah.
And you still had edges that had imperfections in them. You wanted to tie the edges together.
That's correct. The algorithms are, again, different algorithms have different purposes, and you know, I can't cover all the research possibilities or opportunities that have been done. Here, the approach here, the innovation here is to have a local approach to the depth data and global approach to the depth data combined to produce a solution. So this is the main contribution of this. This is how it is different.